Hello everyone, welcome back to the channel. In this video, we will learn about Ollama and we will see how we can create a RAG application using Ollama. So before we start, what is Ollama? So Ollama is a platform and tool designed to simplify the process of running and interacting with large language models locally on personal devices like laptops or servers. It allows developers, researchers, and enthusiasts to use and deploy advanced LLMs without relying on cloud-based solutions, ensuring better privacy, data control, and offline capabilities. Now, what are the key features of Ollama? So, Ollama is provides basically local model execution. So, Ollama enables running LLMs on your local machine, avoiding the need for internet connectivity and ensuring that sensitive data remains private. Ollama is also very user-friendly interface. Ollama often comes with tools or interfaces to make it easier to interact with LLMs, even for those without extensive technical expertise. Now, it also provides customizable models. Users can fine-tune or configure models to better suit specific use cases or domain requirements. Now, it also provides better privacy and security capabilities as since models are executed locally here. So that's the biggest advantage here with Ollama, that models are executed locally. So there's no data transfer to third-party servers, which enhances the data security and compliance. Also, it provides better compatibility with existing tools. Ollama integrates well with various development frameworks and APIs, making it versatile for embedding into applications or workflows. Now, here below is a step-by-step guide on how to create a retrieval augmented generation RAG workflow using Ollama and LangChain. So we will walk through each section in detail, from installing required packages to importing the necessary libraries to implementing the final retrieval and generation steps. So we'll go through all the steps one by one from scratch. Before we begin, we need to ensure that we have the following libraries installed. These libraries make it possible to load and parse documents, split them into chunks, embed text using a transformer model, store embeddings in a vector database, and finally generate responses using the Ollama large language model. So the first one is Ollama. So we have to install pip install Ollama. So now this is a Python client for the Ollama LLM server, enabling local inference of Ollama models. So, next, once we have the Ollama installed, so next we need to pull the model from Ollama. So here we are pulling Llama 3.2. So what does this pulling mean? So Ollama pull command is used to download and cache a specific model from Ollama's model repository. This command ensures that the specified model is available locally for use. That is, it's present locally in our laptop to be used. And how does it help us? So it helps us to eliminate the need to fetch the model repeatedly, or it reduces the dependency on internet connection also during runtime. So once we have the model available in our local, we don't need to fetch the model again and again in the runtime. Now the next one is LangChain. So we have to give this command pip install LangChain. This is the library to implement the chain of tasks, document loading, splitting, vector, store management, etc. So we are utilizing LangChain for these specific tasks here in this code. Now we also have pip install LangChain community. It is a community contributed extensions for LangChain, that is additional vector stores, and provides certain additional features here. The next one is LangChain Hugging Face. This is a integration that allows you to use Hugging Face endpoints with LangChain. We may not be using all of these libraries, but in general, whenever we are using LangChain, it's good to have these packages installed. The next one is ChromaDB. A ChromaDB is basically a vector database for storing and retrieving text embeddings. We are also using PyPDF. PyPDF it's a PDF parsing library that helps extract text from PDF documents. Next, we have sentence transformers. This package basically provides state-of-the-art sentence embedding models. So here we will also be doing some converting the text into embedding. So for that, we will be using sentence transformers or the models from sentence transformers. basically the embedding models. So now after we are done with installing all these required packages, we need to import them into our Python script or notebook. So now we'll see one by one the functionality or the task each of these packages will be doing. The first one is directory loader and PyPDF loader. Directory loader automatically loads all files of a given type, example PDF or text from a specified folder. Okay, so from one folder, it automatically loads all the files. The next one is PyPDF loader. So this is basically designed to parse the PDF files. Next one is text loader. Text loader is useful for plain text files. Okay. Next one is recursive character text splitter. So recursive character text splitter splits large documents into manageable chunks, smaller chunks for embedding and storing in a vector database. So the next one is Hugging Face embeddings. So Hugging Face embeddings is nothing but a wrapper around Hugging Face text embedding models, letting letting you easily generate embeddings from your text chunks. The next one is Chroma. Chroma is again a vector database used for storing embeddings and performing similarity search. We also need to import the Ollama. Ollama is basically it allows us to interact with the Ollama LLMs or models locally, enabling generation from a large language model without relying on external APIs. Okay, now let's move on to the actual implementation. Once we are done with installing the packages and importing the packages. So now let's see the actual implementation. So when we talk about the implementation, the first step is loading your documents from the designated folder. So we have a folder, this folder called as data, and inside this folder we have all the files, all the PDFs. So the first step is to load all the documents from this particular data folder, right? And to do so we are using directory loader, which scans this folder for all the PDF files. Okay, and the next we are using PyPDF loader. The PyPDF loader is then used to extract text from each of these PDF files. And then at the end of the step, we have this variable called as docs, which is a list of LangChain document objects. Now let's see how does this docs look like, right? So it is a list of objects, right? If we see, it has various PDFs which we have in the data directory or data folder, right? Cricket doc 1 PDF, Cricket doc 2 PDF. Similarly, other PDFs. Now the next step is splitting documents into chunks, right? So to handle large text efficiently, we split each document into smaller chunks. Now, how does this help us? This helps us to maintain context during embedding and retrieval. It also prevents from, you know, providing extremely large prompts while interacting with the LLM. Now here, recursive character text splitter breaks documents into chunks. So in this case, the chunk size is 500 characters with a 100 character overlap. So while we are making the chunks, we have an overlap of 100. Okay. Chunk size determines how large each chunk can be in characters. Chunk overlap ensures that we don't lose context between consecutive chunks, right? So once we do this, now let's see how does this text variable looks like, right? So now we have the chunks ready. The next step is creating the embeddings. Embeddings basically converting the text into numbers, putting it into very simple words, right? So we convert these text chunks into numerical embeddings using a Hugging Face model. Here we are using this particular model from Hugging Face. We can also change the model or use some another model if we have a specific requirement, but it should be compatible with the Hugging Face embeddings class. But we can use any other model also, which suits our requirement. Now, once we are done with generating the embeddings or generating numbers out of text, now we need to build a vector store. So with our chunks ready and the embedding model chosen, we store the embeddings in a vector database. So after converting the embeddings, we need to store the embeddings in a vector database. So here we are using Chroma because it's fast and easy and simple to integrate, easy to understand. And here we are putting a collection name, which is optional to give, but it helps to, organize the data better. This step basically indexes each chunk by its embedding so it can be quickly retrieved later, right? So after the step, we will be doing the similarity search, right? Now the vector store is populated. So basically we have made the chunks, we converted the chunks into embeddings, we stored those embeddings into vector store. So now once the vector store is ready, we are we are ready to perform the similarity search. This search finds the most relevant document chunks related to a user query. So once the user puts a query, there's a search which happens in the vector store, and then it fetches out the most relevant chunks based on the query which the user is giving, right? So similarity search uses the embeddings to find the document chunks most similar to your query. Here we have set k is equal to 3, means we retrieve the top three most relevant chunks, right? After this, the results will contain a list of document objects that are contextually similar to the query. So here we can see that, we have retrieved these top three documents which are closest to this query, which is what is supervised machine learning, right? So from the vector store, we have fetched the three contexts, right, which are closest to this particular query using the similarity search. Now we can just combine all these top three retrievals into one. So this step is going to simply join the text content of the top three chunks and results into one coherent string separated by new lines. So we are here basically we are combining all these three retrievals into one, right? So if we see from here, and then we match within the data, right? So title within the data. So now here we have one coherent string out of all these top three retrievals. So once we are done with this step, now we are good to generate a response using an LLM from Ollama, right? So finally, we feed both the user query and the retrieved text data, this particular data variable here, into Ollama's generate function, right? So here we are providing the LLM with the query and the retrieved data or the retrieved text, right, into the generate function of Ollama, right? Now using this, we get a context aware response from the LLM. The model we are using is Llama 3.2, and the prompt basically includes both the retrieved data and the user's query. If you see, data variable is here and the query variable is here, same variable, right? So we have used data and query both to create the prompt, right? So once we pass on these um, arguments or parameters in the generate function, this Ollama.generate function returns a dictionary where output and this key response contains the actual generated text. So now if we look at the response, we have a really well structured response to the question, what is supervised machine learning? So supervised machine learning is a type of machine learning in which an algorithm is trained on a labeled data set and so on, right? So this is how we can use Ollama and models from Ollama to create local RAG applications. By local RAG applications, I mean using the LLMs locally available in your on your device, on your laptop, on your PC to build RAG applications. So this is all in this video. Feel free to ask your questions in the comment section. Feel free to provide your suggestions and feedback. And if you like this video, please subscribe the channel and like the video. Thank you.